Let us begin with the physical states of carboxylic acids. The first 9 members, that is, C1 to C9 of aliphatic carboxylic acids, are colorless liquids with sharp or disagreeable odors. Higher members are wax-like solids and are almost odorless due to their low volatility. Coming to solubility in water, the first 4 members of carboxylic acids are fairly soluble in water. Due to the ability of the carboxyl group to form hydrogen bonds with water molecules, their solubility decreases with the increase in the length of the carbon chain. Higher carboxylic acids are virtually insoluble in water due to the greater influence of the hydrocarbon part. The simplest aromatic acid, benzoic acid, contains too many carbon atoms to show any appreciable solubility in water. Carboxylic acids are soluble in less polar solvents like ether, alcohol, and benzene. Let's now discuss the boiling points of carboxylic acids. The boiling points of carboxylic acids are higher than that of aldehydes, ketones, and alcohols of comparable molecular weights. For example, although acetic acid and N-propyl alcohol have the same molecular weight, acetic acid has a boiling point of 118 degrees centigrade, while N-propyl alcohol has a boiling point of 97 degrees centigrade. This is due to the extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. That is why most carboxylic acid exist as dimers in the vapor phase or in aprotic solvents. Let us now look at the acidity of carboxylic acids. The most characteristic property of carboxylic acids is the one that gives them their name, acidity. Just like alcohols, carboxylic acids react with electropositive metals like sodium and liberate hydrogen gas. Unlike phenols, carboxylic acids react even with weaker bases, such as carbonates and bicarbonates, to form the corresponding salts with the evolution of carbon dioxide. The reaction of carboxylic acids with weak bases clearly proves that they are tremendously more acidic than the very weak organic acids, alcohols and acetylene. Hence, the reaction of carboxylic acids with carbonates and bicarbonates is used to detect the presence of the carboxyl group in an organic compound. Carboxylic acids are much stronger acids than water. In an aqueous solution, a carboxylic acid exists in equilibrium with the carboxylate anion and the hydronium ion, as shown in the equation here. As for any equilibrium, the concentrations of the components are related by the expression Keq is equal to the product of the concentrations of RCOO- and H3O+, divided by the product of the concentrations of H2O and RCOOH. Since the concentration of water remains almost constant, we can combine it with Keq to obtain the expression Ka is equal to Keq multiplied by the concentration of H2O is equal to the product of the concentrations of RCOO- and H3O+, divided by the concentration of RCOOH. Here, Keq is the equilibrium constant, and Ka, which is equal to Keq multiplied by the concentration of H2O, is called the acid dissociation constant. Every carboxylic acid has its characteristic Ka, which indicates how strong an acid is. The larger the value of Ka, the greater is the extent of ionization, and therefore, the stronger is the acid. For example, among the unsubstituted monocarboxylic acids, formic acid with the highest value of Ka is the strongest. The values of Ka are usually very small. Hence, for convenience, they are often quoted in logarithmic form as pKa is equal to negative log Ka. Most pKa values fall within the range of 1 to 14. The smaller the pKa, the stronger is the acid. For example, among trifluoroacetic acid with a pKa value of 0.23, benzoic acid with a pKa value of 4.19, and acetic acid with a pKa value of 4.76. Trifluoroacetic acid with the lowest pKa value is the strongest organic acid. Stronger acids have pKa values less than 1. For example, trifluoroacetic acid with a pKa value of 0.23 and trichloroacetic acid with a pKa value of 0.65 are strong acids. Acids with pKa values between 1 and 5 are considered moderately strong. For example, fluoroacetic acid with a pKa value of 2.66, chloroacetic acid with a pKa value of 2.86, and nitroacetic acid with pKa value of 1.68 are moderately acidic acids. Weak acids have pKa values between 5 and 15. For example, phenol with a pKa value of 9.95, orthocresol and with a pKa value of 10.28 are weak acids. Extremely weak acids have pKa values greater than 15. For example, ethanol with a pKa value of 16.0 and acetylene with a pKa value of 23.0 are extremely weak acids. Carboxylic acids are acidic and readily lose a proton because the carboxylate ion formed by ionization or reaction with a base is stabilized by resonance. According to the resonance theory, the carboxylate ion is a hybrid of two structures, which, being of equal stability, contribute equally. The negative charge is evenly distributed over the two oxygen atoms. Let's now compare the acidity of carboxylic acids with the acidity of phenol. When you compare the resonance structures of the carboxylate ion and the phenoxide ion, you can clearly see that the carboxylate ion is stabilized by two equivalent resonance structures in which the negative charge is on the more electronegative oxygen atom. The phenoxide ion, on the other hand, has non-equivalent resonance structures in which the negative charge is on the less electronegative carbon atom. Hence, resonance is more important in the carboxylate ion than in the phenoxide ion. Furthermore, the carboxylate ion is more resonance stabilized than is the phenoxide ion. This is because a negative charge is more effectively dispersed over two electronegative oxygen atoms in carboxylate ions, less so over one oxygen atom, and the less electronegative carbon atoms is phenoxide. Thus, carboxylic acids are more acidic than phenols. Let us now examine the effect of substituents on the acidity of carboxylic acids. Electron withdrawing groups increase the acidity of carboxylic acids by stabilizing the anion through the dispersal of the negative charge on the carboxylate ion by the inductive or resonance effects. For example, chloroacetic acid with the electron withdrawing chlorine group is 100 times as strong as acetic acid. The acidity of carboxylic acids increases with an increase in the number of electron withdrawing groups. For example, trichloroacetic acid with 3 electron withdrawing groups is more acidic than dichloroacetic acid with 2 electron withdrawing groups, which in turn is more acidic than monochloroacetic acid with 1 electron withdrawing group. The strength of the electron withdrawing substituent determines the magnitude of the effect on acidity. For example, fluoroacetic acid is stronger than chloroacetic acid, which in turn is stronger than bromo and iodoacetic acid. This is in accordance with the decrease in the electronegativities of halogen atoms. The nearer the electron withdrawing group, the greater is the acidity of carboxylic acid. For example, among the halosubstituted acids shown here, alpha-chlorobutyric acid with the chlorine atom on the alpha carbon is more acidic than beta, which in turn is more acidic than gamma-chlorobutyric acid. The increasing order of acidity of some of the electron withdrawing groups is as shown here. Note that in the case of carboxylic acids, in which the phenyl or vinyl group is directly attached to the carboxyl group, there is an increase in the acidity of carboxylic acid instead of the decrease expected due to the resonance. This is because of the fact that the carboxyl group is attached to a more electronegative sp2 hybridized carbon. Electron-donating groups, on the other hand, decrease the acidity by destabilizing the anion by intensifying the negative charge. Thus, among the unsubstituted aliphatic monocarboxylic acids, formic acid with no alkyl group is about 10 times stronger than acetic acid, which in turn is stronger than propionic acid, and so on. In the aromatic carboxylic acids too, electron withdrawing groups increase the acidity, while electron donating groups decrease it. For example, para-nitrobenzoic acid with an electron withdrawing group is more acidic than benzoic acid, which in turn is more acidic than para-methoxybenzoic acid with an electron donating group. The chemical properties of carboxylic acids can be conveniently studied under 5 headings. reactions involving the hydrogen atom of the COOH group. Reactions involving the OH part of the COOH group. Reactions involving the COOH group as a whole. Reactions involving the alkyl group of the acid. Reactions involving the aryl group in aromatic acids. Let us examine the reactions involving the hydrogen atom of the COOH group first. You already know that monocarboxylic acids evolve hydrogen with strongly electropositive metals such as sodium, potassium and calcium, and forms salts with alkalis. This reaction essentially involves the hydrogen atom of the COOH group. The reaction of formic acid with sodium metal and sodium hydroxide is shown here. Note that although the salt, sodium formate, is formed in both the reactions, hydrogen gas is evolved only in the reaction with sodium. Monocarboxylic acids, being stronger than phenols, react with weaker bases such as carbonates and bicarbonates to form the corresponding salts with the evolution of carbon dioxide. This reaction is used to detect the presence of a carboxyl group in an organic compound. For example, in the two test tubes shown here, test tube A contains acetic acid and test tube B contains phenol. When sodium bicarbonate is added to both the test tubes, you can see that effervescence is observed only in test tube A and not in test tube B. The reaction of acetic acid with sodium bicarbonate is shown here. Thus, this reaction can be used as an identification test for the carboxyl group. Now let's examine the reactions involving the hydroxyl group. The hydroxyl group in carboxylic acids behaves like alcohols and can be easily replaced by groups such as OCOR, OR, NH2 or Cl to form anhydrides, esters, amides and acid chlorides respectively. Let's look at each of these reactions in detail. On being heated with a dehydrating agent such as phosphorus pentoxide or with mineral acids such as sulfuric acid, carboxylic acids give the corresponding anhydride. For example, acetic acid, on heating with phosphorus pentoxide, loses a water molecule to form acetic anhydride. Carboxylic acids react with alcohols in the presence of a mineral acid catalyst, such as concentrated sulfuric acid or dry hydrochloric acid gas, to form esters. Reaction is reversible in nature and is known as esterification. For example, acetic acid reacts with ethyl alcohol in the presence of concentrated sulfuric acid to form ethyl acetate. The esterification of carboxylic acids with alcohols is a nucleophilic acyl substitution reaction. The steps involved in the mechanism are: the first step is the protonation of the carbonyl group. In the presence of mineral acids, the carbonyl group of the carboxylic acid accepts a proton to form a protonated carboxylic acid, as shown here. The second step is the nucleophilic attack by the alcohol molecule. Due to the protonation, the carbonyl carbon becomes more electrophilic and is therefore attacked easily by the electron-rich oxygen atom of the alcohol molecule to form a tetrahedral intermediate. The third step is the loss of the water molecule. Proton transfer in the tetrahedral intermediate converts the hydroxyl group into an H2O plus group, which, being a better leaving group, is lost as a water molecule. The result of this step is a protonated ester. The last step is the loss of the proton. The protonated ester thus formed finally loses a proton to give the ester. The OH group of carboxylic acids is replaced by a chlorine atom on being treated with phosphorus halides or thionyl chloride to form acid chlorides. The reactions of acetic acid with phosphorus trichloride, phosphorus pentachloride or thionyl chloride are shown here. Note that although acetyl chloride is the main product in all the three reactions, the byproducts vary. Thionyl chloride is preferred because both the byproducts, sulfur dioxide and hydrogen chloride, being gases, escape the reaction mixture, making the purification of the products easier. Carboxylic acids, when treated with ammonia, form ammonium salts, which upon heating lose the water molecule and forms amides. For example, acetic acid reacts with ammonia to form ammonium acetate. On being heated, this ammonium acetate loses a water molecule to form acetamide. Similarly, a dicarboxylic acid such as phthalic acid forms ammonium phthalate on reacting with ammonia. On heating, ammonia phthalate loses two water molecules to form phthalimide. When this phthalimide is heated further, it loses an ammonia molecule to give phthalimide as the final product. Let's look at the reactions involving the COOH group as a whole. The first one is the reduction of the carboxyl group. Carboxylic acids, on reduction with lithium aluminium hydride or diborane, gives primary alcohols. For example, acetic acid, on reduction with lithium aluminium hydride, gives ethyl alcohol. The second one is the decarboxylation reaction. Sodium salts of carboxylic acids, when heated with soda lime, loses carbon dioxide to form hydrocarbons. This reaction is known as decarboxylation. For example, sodium acetate, when heated with soda lime, gives methane. Cole's electrolysis of sodium or potassium salt of carboxylic acids give hydrocarbons with twice the number of carbon atoms present in the alkyl group of the acid. For example, the electrolysis of a concentrated aqueous solution of sodium acetate gives ethane at the anode. The other set of reactions are the reactions of the alkyl group. Carboxylic acids with an alpha hydrogen react with chlorine or bromine in the presence of a small amount of red phosphorus to give alpha halocarboxylic acids. This reaction is known as Hell-Volhard-Zielinski reaction. For example, propionic acid on reaction with chlorine in the presence of red phosphorus gives alpha-chloropropionic acid. Finally, the reactions involving the aryl group in aromatic carboxylic acids. Aromatic carboxylic acids undergo the usual electrophilic substitution reactions of the benzene ring, such as nitration and sulfonation. The COOH group, being a meta-directing group, directs the incoming electrophile to the meta position. Furthermore, as it is a deactivating group, the reactions occur only under drastic conditions. For example, benzoic acid, on heating with a mixture of concentrated nitric acid and concentrated sulfuric acid, gives meta-nitrobenzene. It is important to note that carboxylic acids do not undergo the Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst, aluminium chloride, which is a Lewis acid, gets bonded to the carboxyl group strongly. Let's see the important uses of carboxylic acids. Methanoic acid is used as a coagulating agent for latex in the rubber industry. It is used as an acid bath in the textile, dyeing, and electroplating industries. It is used for the dehydration of hides in the leather industry. Ethanoic acid is used as a solvent and as vinegar in the food industry. It is also used in the manufacture of plastics and rayon. Hexane 1,6-dioic acid or adipic acid is used in the manufacture of nylon 66. Esters of benzoic acid are used in perfumery. Sodium benzoate is used as a food preservative for fruit jams and juices in the food industry. Higher fatty acids are used for the manufacture of soaps and detergents.